So beyond annotation, what is often done is to use large cancer sequencing studies to try to statistically implicate what are the drivers of cancer growth by looking at many different tumors. So this brings us to the key distinction, which I alluded to a little bit in the last module, is that there's two types of mutations that we're going to think about. We're thinking about driver mutations. Those are the cancer-promoting mutations that provide a selective advantage for cancer cells to grow more than they die, so they help the tumor eventually grow. And then there's passenger mutations, which either don't provide any benefit or actually may adversely impact how well the cancer cell could grow. And what we're going to be focusing in on is, can we understand what are the relevant genes that contain driver mutations? And so we call that cancer driver genes, where as a gene containing one or more of these driver mutations. So if the gene is mutated, it's going to help promote the cancer growth. And generally we think about two different types of cancer driver genes. One being an oncogene, which requires gain-of-function mutation. So when the gene is mutated, it either is more active or gains an entirely new function that allows it to promote cancer. So it's like almost like you had a stuck accelerator where you're constantly going forward and it's promoting cancer growth. The second set is tumor suppressor genes. So these are the ones where mutations would inactivate the gene or lose its function, and then it would no longer be able to restrain cancer. So this is more like if you had a brake, you remove the brake and you can't stop. So cancer sequencing studies are just trying to, well, at least one purpose of them is to assess a large number of tumors to detect genes with significantly elevated number of mutations in them, as they're likely candidates for being driver genes. All right. So there's some challenges when you're trying to do this sort of analysis, statistical study, to identify and implicate cancer driver genes. One of the large issues is that most mutations in cancer are actually passenger mutations, so they're the neutral type of mutations. So you have this difficult task of distinguishing between many neutral passenger genes and mutations from the very few cancer driver genes. So for example, often if you just look at a single type of cancer, you may come up with 20 to 50 cancer driver genes being active in that tumor type. But the whole genome will, even for just protein coding genes, have more like 20,000 protein coding genes. So you have much more other genes that aren't necessarily playing a central role to cancer. So you really need to make sure that you have very little false positive rate or type 1 error to make sure that most of the genes that you implicate are actually going to be real driver genes as opposed to statistical artifacts. So the typical way in practice to control this error rate is to use the false discovery rate through a method called the Benjamin-Hochberg procedure. So now we get into trying to understand how one does this statistical test of trying to implicate cancer driver genes. So one approach is simply asking the question, are there more mutations than one would expect by chance in a gene? And one early method that did this is called MUSIC, developed at the Washington University in St. Louis. And what they did was they modeled the rate of mutations that accumulate in tumors, and specifically the rate of mutations that happen per base, since each base could have possibly been mutated in a gene or not mutated in a gene. So if you look at here, for example, if you just had a gene that had length L, each one of these bases in any given tumor could possibly have observed a mutation. So you have L bases where you could have observed a mutation. But for a cancer sequencing study, since you're sequencing many tumors, you've not just sequenced this gene one time, but if you have T different tumors, you've sequenced it T times. So in total, the number of bases you have that could have been mutated in a large study is the number of tumors T times the length of the gene L. This forms the basis at risk that you could potentially see mutation. And so with this, the statistical test for evaluating mutation rate is then just simply you have some background rate by chance of acquiring mutations, and that's denoted by the variable mu. And then the alternative hypothesis is that actually there's an elevated rate of mutations greater than mu, potentially indicating that these mutations were important, so cancer reuse these over and over again across several different tumors. So for a particular gene, perhaps you see K mutations. You want to then generate a p-value corresponding to the statistical significance of seeing that number of mutations. So in this case, for music, they used what's called a binomial model. So they want to evaluate what's the probability of seeing K or more mutations given our mutation rate. One sort of computational trick you do instead of counting from K to N is actually, it's just more computationally efficient to start counting from no mutated bases to K minus 1, and then take the complement of that to get the corresponding p-value for seeing that number of mutations in a particular gene. And so once you do that for one gene, you can do that for all the different genes that you see in your study, and then correct by using the false discovery rate to come up with a list of statistically significantly mutated genes that you might believe are likely cancer driver genes. However, the model I went over is a little bit simple in the sense that we had assumed that there is one constant mutation rate across cancer. But in actuality, you have variable mutation rate. And this can happen at different spots of the genome, can happen in different types of cancers, and can happen for different DNA changes. So this is shown in this plot here, where various cancer types are shown on the x-axis, like for example rhabdoid tumor here, and then on the y-axis is the mutation rate shown here in per megabase. And what you see is actually the median of different cancer types on a log scale could be vastly different between two different types of cancer. So for rhabdoid tumor, its mutation rate is about more 0.1 on average mutations per megabase, while in melanoma, it's more than 2 orders of magnitude higher. So there's much more mutations. And even if you look within a single type of cancer, each sample here, tumor sample here being a dot, some tumors will have much higher mutations than other tumors in the same cancer type, indicating that from patient to patient, you're going to observe very large ranges in terms of the number of mutations you see. In addition, mutation rate is known to vary by what is the particular DNA changes and what's the sequence of context around a mutation. So this is shown in the bottom panel here, denoted by different DNA changes being different colors, and it's showing the fraction of mutations that are generated from, say, in yellow, C to T mutations. And so you can see on the far end, which represents melanoma, it's actually mostly yellow, reflecting C to T mutations. And so this makes sense because in the case of melanoma, different from other cancer types, you have more of a unique setting where you actually have sun exposure, and you can acquire DNA damage related to UV radiation, causing thymidine dimers and resulting in a specific mutation that you see in the tumor genome. So this leads us to want to develop a model that probably is a little bit better, that captures some of these intricacies. So one adaptation that was used by Music was, instead of considering the mutation rate as purely global, they've developed models for multiple sequence contacts. So you may have a strand-specific model where you model the mutation rate of bases that are T's, that are A's, that are C's and G's, knowing that perhaps they're different from one in each other, and you're trying to account for these differences. And so that's shown here by the updated equations. By now you have a subscript C representing there's different contacts. So now the gene length is now reflecting the number of bases that is specific to, say, A bases or so forth. And then the bases at risk for potential mutations are now also updated. The number of tumors sequence doesn't change, but now you have LC times T as opposed to just purely the gene length. And one other adjustment you can do, going back to previous modules, is to adjust for sequencing coverage. So some DNA bases from your sequencing runs may not have had enough sequencing reads to adequately call mutations. So you can subtract out the bases that don't actually have the potential to have a mutation call. And then you're left in a similar setup where you're trying to have a model of there's a background mutation rate, now contact specific, and compared to whether the number of mutations is going to exceed that expected mutation rate. So similarly here, you can calculate a p-value for each sequence contacts. The issue then is you have multiple p-values for the same gene, and ideally you want to understand you want to have one p-value for the significance of a gene and not, say, 4 in this case. So one approach used by Music was to use a Fisher's combined p-value test to combine, in this case, 4 different p-values into a single p-value. And to do this, they assumed that the p-values were independent of each other, and then calculated the sum of the log of the p-values for the different contacts, where the capital C is the number of contacts you used, and multiplied by -2. And this test statistic can then be compared to a chi-square distribution to generate a combined p-value reflecting the 4 models. And then you can subsequently correct for the false discovery rate to get your list of significantly mutated genes which you think may be implicated in cancer. So I went over the model Music, how there still are some issues which I had pointed out that weren't necessarily explicitly modeled, and so later methods had fixed some of those issues, like the method called Mut6CV adjusted for variation of the mutation rate across the genome at different positions, in addition to being sequence context specific. And other models, including a method I developed myself called 2020+, tries to leverage a different type of approach using machine learning to capture different patterns of mutations that are typical of oncogenes and tumor suppressors. And a recent study from the Cancer Genome Atlas, which I was a part of, tried to use these more newer generation approaches to statistically implicate cancer driver genes. And in this case, our study found that there was 299 cancer driver genes across 33 different types of cancer. And you can see the different genes plotted in what's called a circus plot on the right. And so each wedge here is just a particular cancer type. So in this case, this is bladder carcinoma. And the black text is different gene names that were found to be significant. And if a gene is listed with only a specific type of cancer, it's a cancer type specific cancer driver gene, at least from what we could tell. And interestingly, of these 299, approximately half, as you can see by the circus plot and the genes, are actually cancer type specific, meaning perhaps they contribute to the genetic heterogeneity that you see among different types of cancer. There's also cancer driver genes that are seen in multiple cancer types that are commonly used over and over again. So this is a case for genes like TP53, KRAS, or PIK3CA. They're often seen in many different types of cancer. There's also a set of cancer driver genes that play more of a role in a similar subset of cancer types. So this is the case for squamous cell cancer types, so from squamous cell origin. They shared a subset of cancer driver genes, also for gynecological cancers and gastrointestinal cancers. So what we've found from these cancer sequencing studies is actually that many of the relevant genes are actually only mutated in a relatively small percentage of patients' tumors. So if you look in this case at a study from prostate cancer, the most mutated cancer driver gene implicated is TP53, the gene I was just talking about. But if you look at the mutation frequency, it's only near 20%. And you have along here many other genes which form a long tail of infrequently mutated genes, often below 5% or 2 to 3% of being mutated in tumors. And so this would suggest that given there's so many of these lowly mutated cancer driver genes, that if you consider them in aggregate, they actually play a substantial role in a good proportion of patients. So this leads one to start thinking about that the interpretation of a patient's tumor genome will need to be increasingly personalized, since they may have unique or rare driver mutations that haven't been seen that much before, even in large cancer sequencing studies, but if you could interpret them in terms of a block and make decisions based on that, you could make much more actionable decisions than you could before. Lastly, I want to acknowledge Shirley Liu for allowing me to present this lecture, and then help from Rachel Karchin and Nusheen Nicknaps at Johns Hopkins for helping me prepare the slides. Thank you.